Why can two solid pieces of metal become one, just by making them glow for a moment? And why do some welds look like perfect stacked coins, while others crack apart? Welding works because you're not gluing metal together, you're rebuilding the metal itself across a seam. You create a tiny pool of liquid metal, let atoms mix from both sides, then it cools into a single continuous piece. MIG and TIG are two popular ways to create that same fusion. One is built for speed, the other for control. At the microscopic level, solid metal is a packed crowd of atoms locked into a crystal structure. When you heat the joint enough, that structure breaks locally and turns into liquid. In that liquid state, atoms from the left and right sides can flow together, so the boundary line starts to disappear. Then cooling happens fast. New crystals grow as it solidifies, and the seam becomes a new piece of metal with its own grain structure. But welding doesn't only affect the puddle. Around it, there's a region that got hot enough to change the metal without melting it. That's the heat-affected zone, and it's why welds can be strong, or become the weakest point if the heat history is wrong. Here's the problem: molten metal is chemically needy. The instant it's liquid, it wants to react with oxygen and nitrogen in the air. That reaction creates oxides and contamination that can trap bubbles, weaken the bead, and turn a shiny weld into something brittle. So welding always includes a defense system, shielding. Sometimes it's a cloud of inert gas that wraps the arc and the puddle like an invisible helmet. Sometimes it's flux that protects the surface as it melts. Either way, the goal is the same: keep the liquid metal clean long enough to solidify into a strong, continuous structure. MIG welding, also called gas metal arc welding, uses a continuously feeding wire as the electrode and filler material at the same time. That wire becomes the supply line of new metal, delivered non-stop into the puddle. That design is why MIG dominates in fabrication and production. It's fast. It's efficient. And once it's set up correctly by trained workers, it can lay down long beads quickly and repeatably. The trade-off is that MIG is less surgical. You're feeding metal continuously, so the puddle can be more energetic. That can mean more spatter, less delicate control on thin edges, and more sensitivity to contamination or awkward joint geometry. But for thicker steel, frames, and high-throughput work, MIG is the workhorse. TIG welding, gas tungsten arc welding, flips the philosophy. The electrode is tungsten, which doesn't melt into the puddle the same way. So the arc is like a precise heat tool, and filler metal can be added separately when needed. That separation is why TIG welds can look so clean and controlled. You can shape the puddle, manage how heat spreads, and place filler exactly where you want it. This is especially valuable for thin material, stainless steel, and aluminum where appearance and precision matter, and where mistakes show up instantly. The trade-off is speed. TIG is slower, demands more coordination, and is less suited to high-volume production. It's the scalpel, not the nail gun. So what's the real difference between MIG and TIG? It's not which one is better. It's what you're optimizing. MIG optimizes for continuous deposition. The system is designed to deliver metal quickly and keep moving. TIG optimizes for independent control. Heat and filler aren't forced to move together, so you can make the puddle behave. That's why you'll often see MIG in automotive structures, heavy fabrication, and general manufacturing, places where speed and consistency pay the bills. And you'll see TIG where the weld is part of the product's identity, clean stainless work, precision parts, and situations where you want maximum finesse and minimum mess. Most weld failures don't happen because welding is weak. They happen because the fusion zone is compromised. Porosity is one example, tiny bubbles trapped inside the bead, like a chocolate bar full of holes. Lack of fusion is another, when the bead sits on top without truly becoming one with the base metal. Cracks can form when the cooling and stresses are wrong. And distortion happens when heat shrinks metal unevenly, bending parts out of shape. A good weld isn't just pretty on the surface. In cross-section, it shows consistent fusion, a smooth transition into the base metal, and a structure that looks intentional, not accidental. If you're building fast and strong at scale, MIG is usually the practical choice. If you're building clean, precise, and controlled, especially on thin or sensitive materials, TIG is often worth the time. So welding is really the art of controlling a tiny moment of liquid metal, then freezing it into strength. Now I'm curious, what do you want me to break down next? Stick welding, spot welding, or laser welding?